If you click on that, you can make him a host.
Okay, on my, what, 3 dots? I don't have.
Well,
3
go to
dots.
his picture, go to his frame, and in the upper corner, there should be 3 dots.
If you move your mouse over his picture,
Yeah.
you'll see 3 dots in
Okay.
the upper right-hand corner of his picture.
My problem is I don't have any of the people. They're jumping back and forth instead of, where's
All
my
right, if I talk,
gallery?
maybe I'll pop up.
Okay, but I need to make it gallery somehow.
Yeah, go to gallery view. That's in your upper right corner. It says speaker view or gallery view.
Ah, yes. All right, gallery. Yay. Okay.
And then click on his picture.
Yeah. I'm sorry, I lost it again. Adrian?
No,
No.
Steve.
No,
Steve.
Steve.
Patel.
Okay.
Steve. The other Steve.
All right,
The
got
quiet
it.
Steve.
Finally. Make host. Change host. You're now the host.
Can you see my screen?
Yes.
Yes.
Okay, I gotta get this out of the way. All right, it's really pretty straightforward. What it is can you, on the left-hand side here, I just set up a Monte Carlo type simulation with this game.
We're
And
not seeing the screen, Steve.
You're not
Yeah.
seeing my screen. All right.
No.
Dark, too dark.
Picture.
No. We're not seeing what you want us to see.
All right, I've got share screen.
Click on it.
Oh, I got it. Okay, share. Sorry.
No. Now you got it.
Got it.
Now, yeah. Okay.
Okay.
Now we got it.
Perfect. All right. So what I did is, again, this Monte Carlo simulation, and at the top of it, it says the number of games with each approach. So, and I'm going to vary that. And this is what, to me, made some interesting sense. So one of the approaches is to just stay with my original guess. The second approach is to switch from my original guess to the opposite. And the
Excuse
other
me,
is,
Steve, excuse me. Could
Sure.
you establish the premise first? Make sure
Okay,
we're all on the same page.
right, we're playing the Monty Hall Let's Make a Deal game. So there are 3 doors sitting in front of you. And you have a choice of selecting door number 1, door number 2, or door number 3. One of those 3 doors has a car, using Bob's earlier example. 2 of the doors have goats. You don't know which one has the car or which one has the goats. You obviously want the car. So the host lets you make a original suggestion. And the host says, which door do you think has the car? And you pick a door. The host then, knowing actually where the car is, he selects or she selects another one of the 2 doors that you didn't select and reveals that door to you. The one they reveal is always a goat, because they're not going to reveal the car. And I don't think they did it that way, but at least that's not how this was set up and discussed last time. So you now see that one of the doors you didn't select had a goat behind it. You still have your door, which you selected, and that is your current choice, and the other door, which you don't know what is behind it. And so you have a choice of either staying with your initial random guess, switching to the alternative door, which would be to switch from your initial guess, or you could actually just flip a coin and say, I don't know, because as it was brought up, there are only 2 doors, it's behind one of them, I'm just going to flip a coin and see what happens. And so that's what this first piece of data describes. And it shows here that right now I'm saying we're only going to play one game. I only get to do this once. And I think that's what the psychology of this boils down to, why people are sitting there and they're all excited and they think they might win a car. They only got one chance. So, and what I've shown here is the first game that I've described the result of, there was one chance. And if they stayed, and this actually is three different games. This particular player stayed with it and they actually won. This particular player switched from the initial guess and they won. And this particular player flipped a coin, and I honestly, I should describe here whether it was a stay or switch, but they didn't win. And so that was three different players that got up, played the game, and two of them won a car. One guy, a girl, didn't win a car. So this replay allows me to just change that again. If I do it again, three new players come up. This one actually stayed, they didn't win. This one switched, they didn't win. And this one flipped a coin and, oh, they happened to win. And I can do this over and over. This time, all three of them didn't win. And this time, two of them won. And that time, and so this is what you actually see when you're sitting in the audience or you watch this show. This is kind of what happens. So, okay, now to start understanding how probability works, I can move this up here a little bit. And now, let's say what happens if 10 games are actually played. This person gets to play 10 games. And by 10 games, in this case, they would win 3 times. The person who switches wins 7, and the person who flips a coin wins 3. And I can do this over and over and over. And you start seeing the person who switches from their initial guess almost always does better. And these are all very different games. They're absolutely, everyone's unique. Although, wait a second, this time, the probability was the person who did the initial switch only won 3 times in their 10 games. This person won 5. So then we go, okay, let's just start coursing this up to 100. Now, if we do 100, and this is where it starts kind of getting interesting, because now the person with the initial random guess, they stay, you can start to see what kind of numbers they have. 30, 31, 30, 30, 41. The ones who are switching, they're getting up to 68, 74, 75. And the one who flips the coin, just like one's intuition kind of says, you're going to win about half the time. You're either stay or switch, but you're not making a decision based on anything other than flipping the coin. And if we move it up to, let's see, that's 10,000, and we keep replaying it. Now you start seeing about 50%, 66, 67%, 33%. And so the law of probabilities start manifesting themselves very directly. And if you go all the way up here to, I guess, is that the 100,000, you just see it all over again. So your intuition tells you, well, wait a second, I got to guess one way or another. You're going to win about 50% of the time. If you stay with your initial guess, if they give you 100,000 chances, 33,000 times, you're going to win. But if you switch every time, you're going to win 67,000. So that was, and again, this was just a little experiment on my part. And I am working on a whole, the exploratorium, as you might imagine, they're going to have to really rethink here for the immediate future how they do what they do, because it's a very hands-on place. Everything, it's all designed for you to touch what's there. So the people who are working in the group I work with is called New Media. They're trying to figure out other ways of doing things. And I've got all kinds of things like that. And on the last one, I'll show you if you want to play another game. And this is if you're really interested in mazes. And this isn't a game, but if you want to, this is a maze drawing and solving. But if you're interested in all different kinds of mazes, or you just want to drive yourself crazy, you can stare at this for a while. So that was my 2 cents. And whether it makes sense, I hope it did. I think it expresses here what you see. And for every, no matter how many 100,000 games you run, all uniformly distributed random numbers, every one of them is set up that way, you find the same result.
Yeah, I first ran into this problem maybe about 10 or 15 years ago. And it was exactly the fact that I ran it the way you just did that got me to start learning about Bayesian probability.
So you can
Steve-
unshare me and go with it. Oh,
Steve-
I don't know if that clarified anything.
Steve, this is art. That was terrific. Thank you.
Yeah, that was wonderful.
Yes, thank you very much.
Well, could I ask a question about that, Steve?
Sure.
Where did you get your original data from?
Oh, it's not data. That every time, that's not data. When it did 300,000 games in that every time I click that. It's a computer program that is actually running that is it uses random number generation. And in using that random number generation, it goes through each time and it runs each separate game, and then it runs each separate game 100,000 times, and it just displays the result.
Okay,
So
it's
that's
just
no data. That data was generated. There are numerical algorithms which allow you to generate random numbers. Some are a little better than others. This was a canned numeric, uniformly distributed random number generating program. And it is. It would, if you sat there and flipped a coin 300,000 times, you could have generated this same result.
Okay, Steve, you're going to have to make me the host again.
I unshared my screen. I clicked something that
No,
said,
that's not what I'm asking. I'm asking you to make me the host.
okay, and I do that by saying
Click
what?
on his picture
On his picture. Got it.
and upper right corner.
Okay, I see his picture. I see the make host. Got it. You are now the host.
Okay, thank you. Great. Okay, well, I am now going to share my screen. And okay, this is where we were at the end of last week. And because I had spent as much computer cycles and as much time putting this together, I'm going to finish up what I said last time and then move on to this week's lecture.
Did you hit record?
Yes, I did. I started before we did the Monty Hall stuff. Okay, so we have this 100,000 die, and we're going to do 1,000,000 steps to watch how it evolves over time. And we're trying to understand how equilibrium works. Whoops. So the first 100,000, even if you take a look at a small one, it still looks pretty small. As you keep going, the number starts heading towards the equilibrium rate of 50,000, and the little red square shows that it's not smooth the way it looks. It shows that square up on the upper left-hand side, and it keeps getting more and more close to the equilibrium rate. I'm up to 750,000 steps, and now 800,000, 850,000, 950,000, and it's just going to keep going. So the thing that we've been trying to do is to understand these macro canonical events, and what you're seeing is that there is a equilibrium level that the continued sampling and changing of the die never moved from the equilibrium line. There's just so many different possible ways that you can be there that you can hardly ever move from that. Not that you can't, but you can. We did this in a way to try and model the way real systems do, at least in terms of having 6 dimensions for each particle. So we had a die that had 6 numbers, which were mapped into 0s and 1s. And whenever I did a actual, I chose what rotation to do randomly, but the rotation itself was always either in the XY plane, the XZ plane, or the YZ plane. And each rotation was discrete, 0, pi over 2, pi, or 3 pi over 2. And so everything was deterministic in the way in which the actions were done. Only the choices were random. And that's very similar to the way in which thermodynamic systems work. You're dealing with particles that are moving around in space. They have positions, they have momenta, and they can change around, but everything is physical. We just don't know what is happening. So, as I said, I think last week, or I hope I did, the word, we're calling these MCs macro ensembles, and they, the definition of an ensemble was done initially, I think, by J. Willard Gibbs in 1902. It's an idealization of a large number of virtual copies of the system, and you consider them to all possible realizations for the systems that you're dealing with. And if you assume that the probability of each one is 1 over the number of possibilities, then you have a probability distribution. Okay, we've talked about collections of individual particle behaviors and behavior of the entire system. And the idea of having a collection of individual particles behaving as a system is called coarse graining. And in our simple models, we simply summed up all the number of upward facing dice, and that was our coarse graining. And we'll talk a little bit more about this later. Okay, I think I just talked about all of this, so I'm going to pass on. It is always possible that every single time I randomly chose, every one of them could have turned out to be a XY plane rotation. That would never, if that happened, it would have always provided leaving the top die exactly where it was. So if they were all at 0, the million steps would have been always 0. However, how many particle behaviors would have that taken? Well, you have 100,000 die, you have a million tries on doing that, or about 100 billion of those. And for each one of those, we had we would have had to have chosen 1/3 for the x, y, y, z, and z, y plane, and we would have then chosen any one of the 4 rotations possible. That wouldn't, as long as you always change it, be there. So you would have a tremendous number of rotations always turning out to be exactly the same. That's almost impossible to occur. So for a collection of micro behaviors, the number of possible system setups is just huge. And we were only working with 100,000 particles. In a real gas, you have 10 to the 23. That's 100,000 billion particles, not 100,000. That is a billion times, and a billion times as many as the particles we had in our simple system. So the numbers in a real system are just incredibly huge. I called it huge to the huge power. On the other hand, when you have coarse grain systems, they can also be huge, but only huge to the very large power. So typically, we always look at the macro canonical ensemble. And for this week, which was last week, I'm going to start on statistical mechanics and deal with collections of particles, conserving energy, equilibrium, heat bath, temperature, probability of a particular energy state in a microcanonical ensemble, and the probability is proportional to the energy divided by a particular constant times the temperature. So actually, I won't be able to get there through that this week because my computing, I just didn't have enough time to finish all the way through to that, but I will get through the first 3. Okay. So now what I need to do is share, new share thing. Let me see if I can do this under the okay, let me go back to what I was doing. Switch to the new lecture. Make it full screen. Then go back and share screen, and hopefully now you have the new set of lectures. Everybody can see it?
Yes.
Good. All right, so we're going to skip the abstract because it's always the same, and the introduction is going to do a last version of the small models, then move on to microstates, macrostates, density of states, and other kinds of things leading to the Maxwell-Boltzmann distribution. All right, so we're going to use this one last time for one more, actually 2 more short models. So we have dice have faces 1 to 6, and they're mapped 0 to 1, and we start them all at 0. So in this case, I just choose 100 die, and each one is a position from 1 to 100. So I can map 1 into 0, 0, and 100 into 9, 9. And then just to make the picture look a little prettier, I can jiggle the location so that it looks like it's moving. It's not really, it's just going into a particular space. Okay, did I set that up? I don't think I actually did. Let me go here and where am I gonna go? I'm sorry, I should have been more set up for this. I apologize. I'm slow today. Okay. And we're in Thermo and movies and open that up. Okay. So now let's move that to the beginning and go back to the meeting. And then do a new share onto, here we go. So hopefully you can now see the picture that I have.
Yes.
Okay, great. And now I'm just going to run the meeting. And as you can see, it's going and bouncing around, and it's now already here in just a few hundred steps. We're doing roughly half the number of left versus right positions in the picture that I had showing what looks like adiabatic free expansion. So you start everything on the left and stuff just starts moving around, and eventually half and half. And you don't know which particular button particle. Pardon?
It'll be an hour and a half.
Okay. Anyway, so that's one. Now I need to do a new share. Go back to my original one. Okay. And hopefully now everybody, we're back on the lectures. Is that correct?
Yes.
Okay. So the next thing I'm going to do, I took 1,000 of die, and instead of mapping them into 2 locations, I mapped them into 3 locations. So the picture on the left here now looks like a real box, and the gas are mostly, this is after, obviously I didn't get it quite small enough. So, but this is the first 100 or 1,000 steps. And then you add another set of steps, and lo and behold, you got more coming over to the right and more coming over to the right. And even though the lines look small, I've taken the little square in the center here and put them on here and here, so you can see that these lines are really bouncing around just the way everything is supposed to be doing. And by the time we get to I think this is around 800 or so steps. We roughly at equilibrium. And so we've been able to use a very, very simple model to show how, and it's exactly the same model that we had before, except that every zero was a left and every one was a right. So I changed the zero into a left and the one into a right, and we got the behavior of free expansion of a gas. So very, very simple models can have very similar behavior as adiabatic free expansion of a gas. And I'm going to talk about a lot more detailed information about how it's done in statistical mechanics, but I wanted everybody to realize that these very, very simple kinds of models can behave very much the same as the more complicated ones that we get in statistical mechanics. Okay, so what does it mean to apply statistics to describe a physical system? Okay, so there are a lot of aspects of the system that you could try to compute statistics for. We have to ask ourselves, what is the approach that is most useful? And I'm going to try to use the concepts of statistical mechanics and eventually define quantities like temperature, pressure, entropy. But we're going to start mostly about energy. And although we've talked about all of these things, we'll have to hold our thoughts about these until later. So, an isolated physical system. A physical system exists in a discrete set of microstates, possibly infinite, but discrete. So a microstate defines the values of all possible microscopic variables. And in classical mechanics, that means that every particle is described by its position and momentum. That's Newton's laws. In quantum mechanics, it's defined by the wave function at every point in space. We're not going to do quantum statistical mechanics, but I just want to point out you can actually do it. And if you're going to specify a microstate system, you have to have the most detailed description you will ever be able to care about. So that means including Newton's laws and the way in which they interact with each other. If they have electrical charges, then you have to include Maxwell's equations. So a microstate is not a particular finite specific definition. It depends upon the physics of the system you're dealing with. So sometimes they will include quantum mechanics. Sometimes they will not. Sometimes they'll include Maxwell's equation. Sometimes they won't. For continuous description in classical physics, only Newtonian physics, we're going to use an approximation. We're going to use very small bins for the quantities under description. So we'll take the limit as the bin goes to 0, and we'll get the continuous result. But the initial start we're going to always work with is a finite bin size, and using this is always called a lattice. Now, I can't draw pictures in more than 3 dimensions, or at least I haven't figured out how to do it. So I'm going to simplify to a very, very simple universe. We're going to have 1 dimension of physical space and 1 particle. That's the entire universe that we're dealing with. So the lattice phase space, which is the position and momentum, will have the position bin size delta x, and that'll be the left-right part of the picture. And the momentum particle, the mass times the velocity, is going to be the vertical direction, and we're going to have a bin size of momentum of delta p. This is a different delta because it's a different quantity. So this shows the picture. This is the entire phase space. You have to think of this as 3 dimensions, and if there are 10 particles, then this would be 30 dimensions. And this is one, the way I've drawn it, this is 1 dimension, 1 particle. So the bin size for the space, or the lattice spacing, is delta x for the x position, and delta p for the momentum space. Okay, so the volume defined by the intersection here, this little area is a volume because this is actually 6n dimensional space, so it's a volume, even though it's here only an area. So every 6-dimensional cube, or 6n dimensional cube, can be defined in terms of these little bin sizes, and those make up the phase space of the whole system. The number of microstates of a typical system, which we've been talking about over and over again, is huge. And there is a tremendous amount of detail that we usually don't care about. So if you consider a box filled with gas, measuring the exact position and momentum of every last gas molecule is literally impossible, and you really don't care. Instead, you're typically interested in a small number of macroscopic variables, large things like the total energy of the system, the total number of the molecules, the volume of the space, and pressure and other things. So these are the things that have practical importance. So a macrostate is defined by specifying the value of every macroscopic variable. So there, as I've said, are a huge number of microstates corresponding to the same macrostate. So you might measure the total energy and the volume of a box of gas. And there are an enormous number of arrangements of the individual gas molecules that will all add up to exactly the same energy and volume. So what we know is the macroscopic value. That's because we can measure it. And hence, it has many different possible states, microscopic states, but you have no idea which one. You just know it's one, you know, and in fact, over time, it changes. So they're not even constant over time. But we've been trying to show that if you're in equilibrium, they're all essentially behaving the same way, even though there are just a tremendous number of different ways in which you can arrive at the same macro state. So did I go the wrong way? Yes, I did. Sorry. Okay. The number of microstates corresponding to a macrostate is called the density of states. So you have to take a look at the size, the volume in phase space, count the number of states, and divide by the two of those. And that every one of those that are equivalent for a particular set of macro variables are called the density of states. And this is usually written using a large omega, and the arguments are the macroscopic variables, the things that you actually care about and that you can measure. So that's a complicated statement, at least it is for me. So let's parse it and try to understand it a little bit better. I've assumed that the microstates are discrete. That implies that omega is also a discrete function. Each macro variable can take on specific values, and it's each one of those different sets of variables, the collection of those is defined. I'm sorry, I lost I was getting rid of something off my screen. Okay, so every macro variable can only take on specific values, and it is defined for the collection of the microscopic value. Now, to make life easier, physicists always treat omega as a continuous function, not as a discrete function. And as long as we can, as long as the allowed values of the macroscopic values are sufficiently close together, the total number of states in any given interval will be huge, and you can treat them as being continuous. This is the way in which band theory in semiconductors is done. So this is done many different ways. So I can think of omega as the number of microstates per unit volume in the phase space defined by the macroscopic variables. And we call that the number density of states. Let's try a simple computation, a simple example. So we'll compute omega of E, the energy, for, again, a very simple system that is a single free particle in 3 dimensions. The microstates are defined by how many dimensional phase space? A 6-dimensional phase space. 3 space dimensions and 3 momentum dimensions. Now the energy is the magnitude of the momentum squared divided by 2m. And because it's a scalar, not a vector. The momentum has 3 dimensions because it has a Vx, a Vy, and a Vz. But the energy is the magnitude of that vector, not the vector itself, and squared. And it doesn't depend on the positions. So I can actually, in this case, ignore them. And I'll just consider the 3-dimensional momentum space. So each value of E corresponds to a 2-dimensional surface in this 3-dimensional space. Does everybody understand why that is the case? Can somebody tell me what 2-dimensional surface I'm talking about?
A
Pardon?
spherical surface.
Pardon?
A spherical surface?
Yep. Steve?
Sorry. I waited.
Okay. I'm going to start getting a list and picking cards and asking people out of the list out of this. Yes. So the momentum, the magnitude of the momentum is the radius of a sphere in momentum space about 0. And the surface of that sphere, the area of the surface, is pi r squared. And so the radius of that sphere is the magnitude of the magnitude. So the density as a function of energy is proportional to the magnitude of the momentum squared. That is, it's proportional to the energy. So the proportionality constant in this example depends upon the discretization we've been doing in the momentum and other things, and I'm just going to ignore all of that right now. We're going to do things in proportions. So does everybody follow the example? Art, did does it make sense to you? Art? Adrian, does it make sense to you?
I think so, yes.
Okay, good. Kathleen, does it make sense to you? Kathleen, are you there?
Everybody has to remember to unmute themselves.
Yeah, when I ask questions, you're going to have to unmute yourself. Okay, I'm going to assume, I mean, if you've got questions, please ask about it now. Don't let it go until later.
Is it helpful to describe the units for people to understand what density means?
Well, the problem is that when we get to a real example here, the units are going to be horrendous in terms, you know, they're going to be kilogram meters per second to the, if we have just say 100 particles, we're saying that it's going to be meter kilograms per, let's see.
Bob, if I can just point out, if you divide by the dimensions, well, by the size of a lattice with the dimensions of the lattice, the whole thing becomes dimensionless and it's just a number.
Yeah, it's a number density, right. Right, okay. So it's actually unitless. Okay, so for as a different example, we're going to consider a more realistic one where we have n free particles in 3 dimensions. Again, the positions really don't matter, only the momentum in this particular one, because we have only the density as a function of energy. And for each one of the energy states, the momentum of the collection of all of the particles, all 3n of them, so if we had 100, that would be 300, would have you would simply take that vector of 300 values, dot it with itself, and take the square root, and that would give you the magnitude. Now, that again, for a specific energy, makes a 3n sphere. So it's exactly the same as it was for a single particle, except that we're in 3n dimensions. So we're going to look for a 3n, the surface of a 3n sphere there, and it turns out that the area, the radius is still the magnitude, but it's now got 300 components in it. But the radius is still the same, the magnitude, and the area of a 3n dimensional surface of a sphere is r to the 3n minus 1. So the number density is proportional to the magnitude of the momentum to the 3n minus 1. probably not everybody knows how to do 3n dimensional surfaces, but I looked it up. That's what it is. And since the energy is the momentum squared, this is proportional to the energy to the 3n divided by 2.
This is no longer a sphere though, is it?
Yes, it's a sphere in 3n dimensions.
Doesn't that mean that the momentum all have to be the same though for each of those particles? Or am I missing something here?
No, that's we're talking about the collection of momenta. All 3n of them have a particular energy. Whatever one each individual one has doesn't matter, but the 3n of them put together, all of those have to have a magnitude that is a constant.
Okay.
So you can have one particle with one momentum, particle 2 with a different momentum, etc. As long as they all collect, as long as they all have the same collection of momenta such that the total magnitude of those is a particular constant, okay, then that makes up a 3n dimensional surface,
Okay.
a sphere.
Yeah, I sort of see.
Okay, so you started getting into where I'm going here. So this is the total momentum. So you have the first momentum, which is particle 1, x, y, z, particle 2, x, y, z, dot, 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 down to particle 100, x, y, z. And so any of those collections of momenta that have the same total magnitude having a constant, that represents the spherical surface in the 300 dimensional surface we're talking about, space we're talking about, momentum space, 300 dimensional momentum space. And the rules are exactly the same. You just do dot in them and get the square root, and that gives you a scalar. And that's the radius of a 3n dimensional sphere. And the energy of the system is proportional to the surface of the 3n dimensional sphere, which turns out to be the radius to the 3n minus 1. And since the energy is proportional to the magnitude of the momentum squared, it is proportional to the 3n minus 1 divided by 2 for the energy. So Adrian, not Adrian, I'm sorry, I don't have my, the problem is if I put my list of participants up, okay, Chaz, did this make sense to you? Lukowski, did it make sense to you?
It kind of does, Bob, but let me go back to the previous slide and see if I understand what you're saying there.
Okay. Yeah.
Okay, so the formula at the bottom, my interpretation of that is the number of microstates at that energy, which is sigma E, is equal to that energy to the
Not
power.
equal, it's proportional to.
Sorry, proportional to that energy to the power 3 times the number of particles minus 1 over 2.
Right.
So what that formula is telling us is that the number of states at that energy, and it tells us it's proportional to the number of particles in this, according to this formula.
Well, it actually means, if you see here, the vector P, you have each particle of the 100 particles, and each one has an X, Y, and Z, or I'll call them 1, 2, and 3 in here, okay? So a single vector here has 300 components in it.
And it's, okay.
And so the magnitude of that, you calculate it the way you always do in vector space. You have the vector of 300 components dotted with that, take the square root, that gives you the magnitude. So the energy is proportional to this square, right?
Right. No, that I
Okay.
understand.
Okay. So we have a particular, we've measured the energy. We know its value is a constant. Therefore, this magnitude of the momentum, regardless of what the settings are in here, the magnitude of every possible combination of 300 P's that are in here, they have to always have the same magnitude. And that makes it a radius of a 3n dimensional sphere about the origin in momentum space. Does that make sense?
Yeah, I'm still trying to get my head around this. So this tells me that I have this number of microstates at that energy. And,
Right.
and so you're going to go on and say that a particle could be in any one of those microstates at some point.
Well, since we've measured the energy and we know what its value is, we don't know what the microstates are. We don't know what the 300 components of the momentum is. But we do know that all of the ones that are in the microstate have the same magnitude of that momentum space. So in the 300 dimensional momentum space, you put a radius out, that's a constant. Now you take a look everywhere around the origin, and since it's got the identical same radius, we're talking about a 3n dimensional sphere about the origin. Right?
I guess the thing that is a little puzzling, I realize we're going to get there, but at this point, we kind of have the trivial result that for any realistic system, there's going to be a tremendously large, circa infinite number of potential states for any level of energy.
Yep, that's exactly the case. That's
And so,
why we don't do microscopic calculations, because
yeah,
you only deal with the macroscopic variables like energy.
right. So I guess that what's difficult for my intuition at this point is understanding why we needed to derive this, because I would have bought that just on an intuitive basis that there's an infinite number of potential states. So what is this formulation? Can you qualitatively describe how this formulation leads us anywhere useful? Why not just say it's infinite? Why do I need the e to the 3n minus 1 over 2?
Well, because you actually need to count in omega, you're counting the number of particles, in this case 100, divided by the volume of the momentum space, or actually in this case the surface of the 3n dimensional sphere. So the density of states is what will eventually show us to be the log of that to be the entropy. I mean, that's where we're eventually going to go to.
Okay.
I'm stepping, I'm jumping way ahead, but the log of omega is the entropy of the system. So we're trying to understand how a number of particles exist within a particular volume of momentum space. And the way in which we can determine that is by measuring the energy.
Bob?
Yeah.
Just one thing that might help is if you were to write E as a function of the squares of the components of the momenta, E equal 1 over 2m times the quantity P11 squared plus P12 squared and so on up to Pnn squared, Pn3 squared. That is very similar to a equation for a sphere, but in this case, it's, as you say, it's a sphere in a 3n dimensional space.
Right. So
P is the sum, that P vector that you have on the left-hand side of the equation.
Right. If I had written this out, it would have been the sum of the m sub I 1 to n,
right,
of m p sub I squared. I'm sorry, p sub I squared over 2m for that. And when you do the dot product here, that's exactly what you get.
Yeah.
You wind up getting these individual p sub i's dotted with each other, so you get the energy once you divide by 2m.
Yeah, I just don't want folks to confuse that P vector with momentum of an individual particle.
Right. That's why I'm saying it is a collection. It's got, if n is 100, this is 300 components.
Right.
The first 3 are here, the second 3 are there, etc. The last 100 are here. So this is a 300 element vector. But you're right, that I should have shown that P dot P gives you the energy once you divide it by 2m. And we're assuming here right now that all the particles have the same mass.
Right.
Okay, hopefully that is a little bit better explanation for some people. So I'm going to give another assumption, the postulate of equal a priori probabilities. And this is not always true, but for the systems we're going to be working with, we're going to deal with this being true. So a system has an equal probability of being in any microstate that is consistent with the current macro state. So we said there was a sphere of possible microstates, okay? And in fact, it's a sphere in a 3-dimensional, 3n dimensional space. So every one of those momenta along the surface are assumed to have the same probability of being. So the energy is the macro state, defines what the possible microstates are, that is the sphere in 3n dimensional momentum space. And every one of those microstates along that surface of 3n dimensional sphere has equal probability. Can the assumption be justified? Well, sort of, sometimes. In practice, it works very well for many different cases. There are some theoretical arguments for it, but we're just simply going to make it as a postulate, that is an assumption. We could look at it a different way. An isolated system that satisfies the postulate of equal a priori probabilities is said to be in equilibrium. So we're either doing another definition for the population postulate, or we're defining what equilibrium means. For the systems that I'm going to be dealing with, we're always going to be in equilibrium. Even if they change, we're going to assume that the system is quasi-static. That means that the system changes so rapidly compared to changes in the macro variable measurements that the system reaches equilibrium for each measurement time. So whatever difference of time it can be between we can do a particular measurement, the system can evolve so quickly that it will always be in equilibrium by the time we can do another measurement. So that's the kind of systems I'm dealing with, or what I'm calling quasi-static. Makes life easier.
So Bob,
Yeah.
you're always migrating around on the surface of this 3n dimensional sphere.
Right, and the size of the sphere may change. So
well, the energy would change, right?
Right.
Right.
What,
so, but for fixed energy, if you're in equilibrium for fixed energy, you're just dithering about on the surface of this sphere.
Exactly. Exactly.
But can I make a comment? For an actual system, the particles are not all at the same energy. Some have more energy than others.
Oh, nobody's assuming that they are. It's
No,
just
well,
the sum of the individual energies that.
Remember, the individual particles don't have. Remember, this has a 300 element in it. It's just that the magnitude of the 300 components is constant. Okay, so P1 could change, P2 could change, all of these things could change as long as the total magnitude of all 300 particles, of all 100 particles, has the same magnitude, that is, has the same energy.
As a matter of fact, one would have to change if the other one did, probably.
Well, right. One would change and another one would have to in order to stay there. So, but the point is that you're moving around in this 300 dimensional space on a surface of a sphere, and you don't know what particular collection of 300 numbers is making it. You only know that the radius of that sphere is a constant because the energy is the same. Got it, Bob?
not completely.
Yeah, the sum has to be a constant, not the individual terms that compose the sum.
You could sort of think of it as one particle runs into another one and transfers some energy to that one and loses some energy. And so there, the overall energy is still the same.
Right. Remember, you're dealing with systems that conserve energy.
So go to the next slide. I just have a comment on that. A system a system consists of many particles, I would assume. And when you say that the system is in any microstate,
Any point on that 300 dimensional sphere is assumed to have equal probability.
right? No, that I understand. And that would be, okay.
So
Why do we
When I
care?
talk about a system, am I talking about the average energy of the system?
the measured, the macro state is the energy that you measure.
Okay, so it's kind of like the temperature of the system or something like that.
Right.
But why do we care?
Well, there's a lot of stuff that we need to get to in order to be able to get to Maxwell's, the Maxwell Boltzmann distribution and the velocity distribution and the ideal gas, where what we're eventually trying to get to is to show how all of these behaviors and probabilities of things happening, of how the system evolves, will follow the ideal gas law. I mean, that's where I'm getting to. But we got a lot of steps to the process, unfortunately. It's not, you know, oh, we can make that assumption, therefore it's not that simple. You got to do a lot more steps.
I understand that we have to do a lot more steps, but my more robust question is, if we assumed that only 3 of the microstates were probable, wouldn't we get to the same conclusion as if we assume every one of them is equally probable?
I'm sorry, I didn't understand the first one.
So here we have an infinite number of microstates, and we're saying that they're all equally probable.
Right.
That's going to allow us to use sort of Newtonian calculus to sort of do all this. But if I assumed that there were just 6 microstates, that of all the infinite number of microstates, only 6 of them were equally probable, and it was 0 probability was in B and any of the rest, I wouldn't have to use calculus to potentially do the remaining calculations, and I probably would get to the same conclusion. Yes? No?
I think the thing here is that you'd have to have some force or something physical that makes those other those 6 states that you're talking about, make them the same, make them more probable.
Yeah, you have to make all of the others be 0, and we've said they're all, you know, there's all these possible states that could be, that are on the surface of this 3n dimensional sphere.
If I could make one point, why you care that the probability, or I should say that the number of microstates scales with the energy of the system to a very high power, why you care is not apparent so far, but it becomes apparent when you bring that system in contact with another system and apply that rule to each system. Then you can do some analysis as to what the final state of the 2 systems are, but it all depends on how each system energy scales with the number of particles.
Right. We've only been talking about one isolated system right now, and that's very unrealistic, as I've said many, many times. So we're going to eventually have to define what a heat bath is and how. We've got a lot more work to do. I'm sorry. You're just trying to guess ahead, and it takes a lot more work to get there.
But I think that Steve has put his finger on it. The reason this is important is to go back to the simulation that you did at the very beginning. When we had that adiabatic system and we opened a hole to a vacuum in another chamber, it had to move into that other chamber. And if only a few microstates were probable, it might not move in the same way as if an infinite number, if all of the microstates were capable. It's sort of Maxwell's demon idea that I could have sort of all the particles at one corner of the chamber and they'd never move through the hole to the second chamber.
There'd have to be some sort of a force acting to keep them.
Well, or that all the possible microstates are equally probable, and that would therefore allow for the diffusion into the second chamber.
Yes, that is what is going to happen.
That's what's going to happen. So this assumption is consistent with what we actually observe. We observe that actually happens.
Well, that's why I said, sort of sometimes. There are many cases where it doesn't, but for the ones we're going to be dealing with, yeah, this is the way we're going to deal with it. Okay, yeah, because we're always going to be quasi-static, we're going to be equilibrium, all these things happening all the time. Now, I was a bit careless with my terminology in the previous material. I said that there was a probability of a system being in a particular microstate. Unfortunately, I never defined what that meant. Given a particular system in a particular microstate, it will only be in one particular microstate and not in any other. So what probability are we talking about? There are two approaches that can be used to define probability in this context. The microscopic degrees of freedom making up the system are constantly changing. So if they're at a constant energy, then they're moving around on this 3n dimensional sphere. And it's not because the particles change, but at one instant, the atoms have particular positions and momentums, and the next ones, they're different. So I can define the probability of a system being in a microstate as the fraction of time it spends in that state. And then we can do averages using this definition of probability, which are called time averages. And this was the definition that Boltzmann actually used in developing his H theorem. It turns out there are some problems with that. So we're going to take a look at it in a different way. Instead of looking at just one system, we're going to think of preparing many identical systems. So we have exactly the same number of particles, the same masses, but and we will prepare them so that they have always the same macroscopic values. So the same procedure is setting it up. All of these systems are in the same identical macro state because they have all the same macro variables. But each one is in a different microstate. So we want to do this because we want to have only one system in one microstate. However, I don't know which one it is. So I want to define the probability of the system being in a microstate as the fraction of these imaginary systems that are in that microstate. So I make a system and I have it set up and it has one set of macro variables. The microstate that does that is one of these systems. Then we do it again, we get a different microstate. We do it again, we get a different microstate. We do it over and over and over again with a tremendous number of these. And the set of all the possible systems that have each individual possible microstate are called a statistical ensemble. And the averages computed with this definition of probability are called ensemble averages. That's a hard concept to get. Jack, do you
No, I see the mathematical equivalence.
okay. Adrian, does it make sense to you? You're muted.
You should be unmuted now. Yeah,
Yeah.
makes sense.
All right. Laura? Lee Gale?
Yes, it makes sense.
Okay, good. I'm glad. All right.
Well, I still have a question of your definition of how you're using the word microstate. And that's not an individual microstate. It's the way the particles of a system are distributed amongst the microstates. Is that when you say a system's in a microstate?
It means that each individual particle has some, remember, we've been discretizing the momentum. So there's a finite number of possible momenta that can be. Now, I've talked about it as being on the surface of a sphere, which makes it infinite, but we're actually looking at a finite connection of points on that sphere because I discretized all the momenta. So every one particle can only have a finite collection of X momentum, Y momentum, and Z momentum. And so a microstate has all of the particles with a collection of momenta that are equal to a particular constant, which is equivalent to the energy that we've measured. So, but there could be, you can interchange any two you want in any of these, just as an example, and those will make another microstate. And then you can make two for one and take one down. So you can do all kinds of different combinations of microstates that all have the same energy. So the collection of all of those possibilities is called the statistical ensemble. Does that make sense to you?
Close enough. Yeah, no, I'm okay with it. And when you say that if two particles exchange states, it will be the same microstate, that's assuming you can distinguish between particles.
It's a different microstate.
Well, if you can distinguish between them, but suppose they're electrons and you can't distinguish between them.
Well, I said we're not, you can do it differently when they're not distinguishable, and you can do quantum mechanics, but right now I'm dealing with classical systems.
So you're assuming all the particles are distinguishable from each other.
Right, but that's because we're assuming Newton's laws.
Okay.
Yeah, I have tried to say over and over again, we're assuming Newton's laws, and they're all distinguishable, or at least able to be distinguished in principle in Newton's laws.
Okay.
Bob,
Yeah.
just listening to this discussion, my sense is that some people may still be confused. A microstate isn't something small. Microstate is something that is everything. When you talk about the microstate of the system, it is all of that information that you eventually need to find that one point you are on this sphere.
Right, right. So if there were 100 particles, there would be 300 elements in a single momentum vector. And if there are 10 to the 23, it's 3 times 10 to the 23. I mean, they can be huge, giant spherical systems.
So the microstate is actually a massive definition of the complete state of the system. It is one instantiation, possible instantiation of the state of the system to give you that energy.
You got it. Thank you. I wish I would have said that sentence. That's great. That's perfect. Thank you. I wish I had thought of it myself.
Yeah, and I thank you too, Steve. That was a good explanation.
Yeah, that's...
Don't count on that happening too often.
that was a great sentence. That was just exactly correct. And I wish I had thought of it and put it down here, but I'm sorry, I didn't think of it that way. That's great. That's perfect. Okay. So we talked about possibility of time averages and ensemble averages, and there then would have to be the question of, are these two definitions equivalent? And the two types, time averages versus ensemble averages, they give you the answer emphatically sometimes. Some systems they do, other systems they don't. And for the description of the simple systems that I'm going to consider, we're going to use the following definition. A system for which time averages and ensemble averages are equal is said to be ergodic. And I like the word ergodic. It's Greek for the word work and path. And if you remember our empirical thermodynamic lectures, work and path were very important words and meaning in thermodynamics. So we're going to assume ergodicity. Hopefully this made things a little bit more clear in terms of understanding what's going on. And we'll look at the definition again of satisfying the postulate of an equal a priori probability. uh, in equilibrium. So an isolated system is in equilibrium if the probability distribution of its microstates does not change with time. So all of our small systems eventually got to the point of where they were roughly 50-50. They didn't change, at least not very much, with time. So this was trying to get you a feeling for what equilibrium was like. And we're using the idea of these equal a priori probabilities as a definition of equilibrium, that is, that those probabilities don't change with time. Okay, so I will almost always use ensemble averages instead of time averages because there are some problems with it. But if they are ergodic, then it doesn't matter. So I'm finally ready to move on to get up to the Maxwell Boltzmann distribution, but we have some more work to do. So the first
Bob,
thing,
before you start, could you finish your talk about 5 minutes before the hour so we can talk about what's going to happen in the two following?
yeah, I will get to wherever I get, and we'll call it there. I'm obviously not going to get to all the way through this material, but we'll pick it up next time when I'm lecturing again in a few weeks. Okay, there's really not so much you can say about isolated systems. As I've said so many times, real systems are almost never isolated. They're embedded in some sort of environment. And the interaction with the environment is the reason that they're complex. So we're going to use a simple trick to perform analysis to non-isolated systems. Begin with an isolated system. We're going to assume that the universe is an isolated system, but we're going to split it into two parts. We're going to call them A and B. A is the portion of the system that I really care about. It's what I want to make measurements on. It is what I want to see how it actually has thermodynamics about. B is the environment that's connected to A. I only care about B the way in which it affects A. And B is called a heat bath. So, examples. Part A is the gas contained in a box. Part B is the box itself, including the whole room containing the box. And assuming pretty much that it's at a constant temperature. The second one, part A is in a test tube with chemicals in it. Part B is a water bath containing the test tube at a constant temperature. The whole system is in the third example. Whole system's the air in a room. Part A is the carbon dioxide molecules in the air. Part B is everything else, the nitrogen, the oxygen, other trace gases, etc. So using set theory, we know that the total system, T, is made of A and B, and so it's A union B minus A intersect B. And so the energy of the total system is the energy of the A portion plus the energy of the B portion plus the energy of the interaction portion, AB, the part that are with both of them. The total energy is we're going to use another assumption, which there's so many assumptions in this, it's amazing that they all work, but they do. Anyway, the first one depends only on the microscopic degrees of freedom that make up A. The second one depends only on the microscopic degrees of freedom of B. And the third one is the one that depends on both parts of the system. For the macroscopic value of energy, I'm going to assume that the interaction portion, energy of EAB, is small enough that we can make it ignorable. So we had our energy was 3 parts, and we're going to say that it's approximately 2 portions, just the sum of EA plus EB. Now this should immediately set up red flags all over the place, because if EAB were really 0, the 2 subsystems would not interact at all. I would have 2 independent, isolated systems. Obviously, that's not accurate. What I do want is for them to be what is called weakly coupled. And this is, the interaction occurs slowly, it's not very large compared to the energies of the total systems. So we can, again, with this quasi-static idea, we can use this approximation for the energy. Given that, we can have another assumption, which is the degrees of freedom of A and B are specified independently. So the density of the state factorizes. The number of states of the total is the number of states for the energy of A times the number of states of energy for B. We are going to have to yet another assumption. I'm dealing with assumption after assumption, but I may call it quits after this. I don't know where else I'm going to next. I'll take a look and then we'll see where to quit. Anyway, the previous assumption restricted them from being coupled through the energy function. That's because we said the interaction portion was very small. This restricts the system from being coupled through the definitions of their microscopic degrees.
To the coronavirus, and so that's the next 2 weeks. And the third week, I think Bob Corson will be back and continue his discussion of thermodynamics. The other thing that's going to happen is that Lee Gale will be the host, Zoom host, for the next 2 meetings. I will be the co-host. So when you log in, you're going to have to get a different invitation to the next 2 meetings, which will come from Lee Gale. And So you can log in. Don't use Bob's login, use hers. And I think she's going to set it up so that as soon as you log in, you're part of the meeting. You're not going to go into a waiting room, is my understanding.
Yes, that's what I'll set it up. And Bob, you don't want me to use a password, is that right?
I don't think a password does any good. So
Okay, you'll receive an email either from me or from Bob, and it will have a live link for you to click, which is different than the link you've been clicking on now to get to this meeting. So it'll have a new link and it'll be live. Just click on it and say join, and you should be in.
Great, thank you.
Okay.
Oh, you're back, Bob.
Yeah, for some reason, I guess it must have been my internet or something, because it suddenly started showing me that I was going to be added to a new meeting. And I was going, what the hell is this? And obviously I had dropped out. So yeah, it says my internet connection is unstable. So I'm glad we're finally at the end. Anyway, I will pick it up where I am here
So
next time in about 3 weeks.
Bob is demonstrating what a weakly coupled system is. Weakly coupled.
Yes, that's exactly the case. And I pay.
Yeah, thanks a lot, Bob. In fact,
yeah,
I like where this goes.
Thank you.
Well done.
Thank you, Bob.
Thank you.
Thanks.
Okay, I guess I'm going to end the meeting.
Bob, do you still want me to try to pass along that JavaScript?
No, once I saw what you were doing, like I said,
Yeah.
I had
I
written my own simulation like that
Okay.
10 or 20 years ago or something like that. I don't remember when, but it must have been around early 1970s. So it's more like
Deja
50
vu.
years. Yeah, whatever. I'm so old. Oh my God.
That's okay. Well, actually, I have extra free time now, so I